Hello, my name is Jonathan and I'm going to do my presentation on the excitation-contraction process. So first I want to go over a few terms. The first one is going to be the neuromuscular junction, or NMJ. So this is where basically the muscle cell is innervated by a neuron. The next would be the synaptic cleft, which is inside the NMJ. It's where the neuron connects to the sarcolemma, which is the muscle cell membrane. The next term is T-tubule. Now the T-tubule is an invagination that occurs on the sarcolemma surface, and it actually runs through the duration of a skeletal muscle fiber, but we're just going to look at a cross-section for today. And this little wine bottle shaped thing is called the sarcoplasmic reticulum, and this stores calcium ions that will come in handy when your muscles need to fire. Now, what is the excitation-contraction process? Well, the excitation-contraction process, or excitation-contraction coupling, is the basis for our ability to move our skeletal muscles. Well, whether it be from a reflex arc where we touch something hot or we hurt ourselves, our instinct is to pull away. Well, that would be an example of this process. Other one would simply be if you wanted to pick up a book or take a step forward. So, as with all muscle movements, it starts with an action potential. An action potential is an electrical current that flows through a neuron. It flows down the duration of the axon all the way to this synapse right here called the neuromuscular junction. So what happens is the action potential reverses the polarities, causing it to be more negative on the outside and more positive, more negative on the inside, more positive on the outside, and it leads to a rapid influx of sodium, outflux of potassium, and addition of calcium. The calcium then acts as a messenger which activates these little vacuoles that are filled with calcium ions. They're filled with acetylcholine, which is a neurotransmitter. The acetylcholine is then released into the synaptic cleft and then binds to these receptors. Now these receptors are very important because they lead to the rapid influx of sodium and the rapid efflux of potassium. This signals basically the same thing as an action potential would do in an axon of a neuron. It reverses the polarities, causing it to be much more positive on the inside, and then the current activates the DHFR receptor, or dihydropyrimidine receptor, which in turn activates the ryanodine receptor channel, which basically it uncorks this sarcoplasmic reticulum wine bottle and pours out all of the calcium that was stored in there. Now the calcium then binds to the actual muscle cell, which this is called a sarcomere. It's a repeating unit. It consists of a thin fiber called actin, a thicker fiber called myosin. The fibers that wrap around it are called tropomyosin, and the little golf club shaped things are troponin. Now calcium will bind to the troponin because the troponin is basically like a lock, and it prevents the tropomyosin from moving. Once the troponin has the calcium, it kind of unlocks the tropomyosin and causes it to shift downward. And then the myosin is able to bind to the actin and then perform what is called a myosin-actin cross-bridge cycle. Now the cross-bridge cycle, to think of it with your hands, looks like this. The myosin is bound perpendicularly to the actin. Once the troponin lock is released, it causes the cycle to push this way, pushing inward and contracting the muscles together. This is what happens when the calcium binds to it, and it will continuously happen as long as there is ATP available. This cycle will happen many, many hundreds of times over a period of contraction. So if you're curling your arm like this cycle is happening hundreds and hundreds of times. Then this will continue to happen until you run out of ATP, which would be the same as getting tired, being exhausted, and you can't do it anymore, so then your muscles return to the state of rigor mortis, or acetylcholine esterase, which is an enzyme. It absorbs all of the remaining neurotransmitter that's floating, causing no more sodium to come in, but it also pumps the potassium back in via leakage channels, and thus it changes the polarities back to negative, and then that tells the DHPR receptor to cork the bottle, and then it closes all the calcium that is remaining outside, and then it uses primary active transport to pump the calcium back into the sarcoplasmic reticulum, and this is all using ATP. And then all the receptors close, and then the muscle returns back to its resting state where it's all able to fire again and again if necessary. Thank you for the video, and I hope you enjoyed it.